In the middle of the 20th century, the railroad industry solved a problem that had been limiting locomotive performance for decades. The problem was simple in description and complex in solution. How do you transmit enormous amounts of power from a large engine to the wheels of a locomotive efficiently, reliably, and in a way that allows smooth control across wide ranges of speeds? The mechanical answer, gearboxes, clutches, drive shafts, was reaching its limits. The components were too large and too failure-prone. The solution was elegant. Remove the mechanical connection entirely. Use the diesel engine to drive a generator. Use the generator's electricity to power electric motors at the wheels. Let electronics handle the control. The diesel-electric locomotive was born. 50 years later, mining equipment engineers looked at the same problem in a different context. Ultra-class haul trucks were getting bigger. Their mechanical drivetrains were reaching the same limits that had constrained locomotive drivetrains a generation earlier. The Komatsu 980E is the expression of that solution in one of the most capable ultra-class haul trucks ever built. A machine that carries 363 metric tons per load, powered by a diesel-electric drive system inheriting railroad technology. But before we get into the specifications, we need to understand the competitive context it entered. The 980E did not arrive in a vacuum. Its direct competitors, the Caterpillar 797F and the Liebherr T282C, had already established what ultra-class performance looked like. Komatsu needed to match that performance while bringing its own engineering perspective to the problem. That perspective produced design choices that differ from its competitors in ways more interesting than a simple specification comparison. The Komatsu 980E is a different engineering answer to the same question, revealing the nature of engineering at the boundary of the possible. The Komatsu 980E4, the current production variant, has a payload capacity of 363 metric tons, the same as the Caterpillar 797F and the Liebherr T282C. This convergence is not coincidental. It reflects the physics and economics of ultra-class haulage, the point at which payload capacity and tire technology intersect. Road construction and operational economics make 363 metric tons the practical optimum for this class of machine. The gross vehicle weight of the 980E4, when fully loaded, reaches approximately 592,000 kilograms. The empty operating weight is approximately 229,000 kilograms. The difference between those two numbers is the payload. The ratio of payload to empty weight, approximately 1.6 to 1, is a measure of the machine's structural efficiency. More payload for less machine weight means less fuel burned moving the machine itself rather than the material it is carrying. This ratio has been a focus of continuous improvement through the 980E's development history. These improvements reflect Komatsu's commitment to extracting maximum payload efficiency from the machine's structural design. The tires, 6 of them, each standing approximately 4 meters tall, are massive, enormously expensive consumables. Each tire costs between $40,000 and $50,000 and weighs approximately 5,300 kilograms. Each one is subject to brutal physics, sharp rock fragments, extreme temperature cycling, and constant heavy loading. Managing tire life is a significant operational discipline with significant financial implications. The dimensions are massive. Height 7.6 meters. Width 9.7 meters, length 15 meters. These trucks require no public roads, specially engineered mine haul roads, and site-specific turning radii. Transported in disassembled sections, the 980E begins to diverge from its competitors with its engine. The 980E is powered by a Komatsu SSDA-18 V170 18-cylinder diesel engine. With a displacement of 102 liters and output of up to 3,500 horsepower, it balances power and reliability. Fewer cylinders means fewer components, fewer potential failure points, and easier maintenance access. The operational record across thousands of hours in dozens of mines has validated this engineering judgment. The diesel-electric drive system uses AC electric motors at the rear wheels instead of older DC motors. AC motors are more power-dense and more controllable, allowing for precise modulation of motor performance. They are more reliable, with no brushes or commutators that require periodic replacement. The performance improvement in tractive effort and speed on grade was measurable and significant. And that's not even the most impressive engineering decision Komatsu made with the 980E. The AC drive system of the Komatsu 980E is built around a pair of rear-wheel traction motors, one at each rear wheel position, driving through a single reduction gear set to the wheel. The generator driven by the diesel engine produces three-phase AC power. This power flows through the inverter system, a sophisticated power electronics assembly that converts it to the specific voltage, frequency, and phase relationship required by the traction motors at any given moment. The inverter system is, in effect, the brain of the drive, the component that translates the operator's demand for power into precisely calibrated electrical signals that produce exactly the mechanical output required. The precision of this control is extraordinary. The inverter can modulate each traction motor's output independently, applying more torque to the wheel with more traction and less to the wheel that is slipping. This individual wheel torque control functions as an electronic traction control system, preventing wheel spin in low traction conditions. Wet haul roads, loose material, ice in cold climate operations without the operator needing to intervene. The system responds in milliseconds, far faster than any mechanical or manual traction control approach could achieve. In practical terms, this means the 980E can maintain productivity in surface conditions where a mechanical drivetrain truck would be spinning its wheels uselessly. A wet haul road after rain, a common condition in many mining climates, reduces the available traction between tire and road surface. A mechanical drivetrain truck responds to reduced traction by spinning. An AC drive truck with individual wheel torque control responds by modulating motor output. The difference in productive time between the two approaches, across a mining operation that experiences regular wet conditions, is significant. The dynamic retarding system of the 980E works on a similar principle. The traction motors reverse their function on downhill hauls, generating electricity. This electricity is dissipated through resistor grids on the machine's frame. The retarding force is modulated with the same precision, allowing smooth, controlled deceleration from any speed without using the service brakes. The service brakes are preserved for emergency use. The retarding capacity of the 980E's electric drive system is substantial. It can absorb and dissipate the kinetic energy of a fully loaded truck. Descending a steep mine ramp at operational speed, maintaining a controlled descent rate without service brake intervention. This capability is not just a convenience, it is a safety requirement in mines where the ramp grades are steep. The cooling system for the retarding resistors, the components that convert the braking energy to heat, is one of the thermal management challenges. At maximum retarding on a long downhill haul, the heat generated is substantial, and the resistors must be cooled by airflow sufficient to prevent overheating. The resistor grid is positioned to maximize exposure to airflow during travel, sized with margin for the worst-case thermal loading. The tractive effort advantage of the AC motors, their ability to deliver more torque at lower speeds, was larger than calculations had predicted. The machine pulled harder on steep grades than specifications suggested. The reason was related to the improved thermal performance of the AC motors. They ran cooler under sustained high-load conditions than DC alternatives, maintaining their rated output longer before thermal derating began. On a steep mine ramp, with a full payload, a modest tractive effort advantage translates into a meaningful speed advantage, and a speed advantage on the loaded uphill haul reduces cycle time, and reduced cycle time increases the number of loads completed per shift. The compound effect across a fleet of trucks over a full year of operation is enormous, and this is where things get crazy. Because the 980E's AC drive advantage is not just about the individual truck's performance. It is about what that performance enables at the system level. A mining operation is not a collection of trucks. It is a system. Excavators, trucks, haul roads, processing plant, all interconnected. And the performance of the truck fleet is determined by the system's ability to sustain consistent throughput over extended periods. The 980E's AC drive system contributes to system consistency. The individual wheel torque control reduces variability in wet conditions. The precise retarding control reduces variability on downhill hauls. The AC motor's thermal stability reduces performance variability under high-load conditions. Reduced maintenance requirements of the AC drivetrain reduce the frequency of unplanned downtime events that create disruptive variability. Mine planners report improvements in production plan adherence. The percentage of shifts where the fleet achieves its planned tonnage target. Incremental improvements in plan adherence, compounded across hundreds of shifts, produce annual production improvements that justify the technology investment. Komatsu supports the 980E with Comtrax Plus telematics for real-time health data and dispatch integration to optimize system productivity. The AHS, Autonomous Haulage System, allows 980E trucks to operate without onboard operators in implemented autonomous programs. Komatsu has been developing autonomous haulage technology since the late 1990s, and the 980E platform has been a key vehicle. At mines in Chile and Australia, fleets of 980E trucks operate autonomously, following GPS routes, loading and dumping without human operators. Productivity improvements come from eliminating operator fatigue and operating continuously without shift change delays or individual operator judgment. What surprised mining operators most about autonomous operation was not productivity improvement. It was the maintenance cost reduction. Autonomous trucks are gentler on tires, drivetrains, and structures. The control system does not accelerate aggressively or brake sharply. The result is measurably lower wear rates on mechanical components, a benefit that compounds into significant cost savings. The 980E, with its AC drive precision and autonomous compatibility, is at the forefront of the trend toward autonomous haulage. Real-world deployments include copper mines in Chile and iron ore operations in Australia, validating the machine's capabilities and investment. The Komatsu 980E represents more than a capable ultra-class haul truck. It represents a trajectory toward fully electric mining haulage that the industry is currently navigating. The diesel-electric drive system is already partially electric. The rear wheels are driven by electric motors, managed by power electronics of considerable sophistication. Remove the diesel engine and replace it with a battery pack or an electric connection to the grid, and you have a fully electric haul truck. This is a development pathway Komatsu is actively pursuing. Battery technology, charging infrastructure, and the economics of mine electrification are all evolving rapidly. The 980E's AC drive architecture is compatible with battery electric or trolley-assisted operation. Only the energy source changes as battery energy density improves. The 980E's legacy will be the platform on which fully electric haulage was proven, the machine that carried 363 metric tons on electric motors. The arc of this story, from locomotive technology in the 1990s to fully electric operation in the 2020s, is a compelling engineering evolution, with the 980E at the center. Stand beside a loaded 980E at a mine ramp as it begins its ascent. The AC traction motors engage with smooth, immediate torque. 592,000 kilograms begins to climb. The fundamental insight, that electricity is a better medium for transmitting power than any mechanical alternative, is unchanged. This insight moves mountains. Next, we move to the machine that holds the most extreme record, simply the largest. The Belaz 75710, a machine built in Belarus. Its payload capacity exceeds anything from Caterpillar, Liebherr, or Komatsu. The numbers are the largest in this category, and we are just getting started.